Thermal processes. Objectives. At the end of the lesson, students are expected to know the 4 common thermal processes, know the concepts and equations of the 4 common thermal processes, solve a problem about isobaric process, and lastly is to answer an identification activity. The 4 thermal processes. We have isobaric process, isochoric process, isothermal process, and adiabatic process. The isobaric process is where constant is P. That would be W is equal to P delta V. For the isochoric process, the constant is V, where work is equal to 0. Isothermal process, the constant is T, that would be delta U is equal to 0 for ideal gas. And lastly, the adiabatic process, no heat exchange, where Q or energy is equal to 0. Kindly take a screenshot of these for further uses. Isobaric process, one that occurs at constant pressure. For instance, figure in the right shows a substance, solid, liquid, or gas contained in a chamber fitted with a frictionless piston. The pressure P experienced by the substance is always the same because it is determined by the external atmosphere and the weight of the piston and the block resting on it. Heating the substance makes it expand and do work W in lifting the piston and block through the displacement. The substance in the chamber is expanding isobarically because the pressure is held constant by the external atmosphere and the weight of the piston and the block. The work can be calculated from W is equal to Fs, where F is the magnitude of the force and S is the magnitude of the displacement. The force is generated by the pressure P acting on the bottom surface of the piston area according to F is equal to PA. With this substitution for F, the work becomes W is equal to PA times S. But the product AS is the change in the volume of the material. Delta V is equal to the difference of VF and VI, where VF and VI are the final and initial volumes respectively. Thus, the relation is W is equal to P delta V is equal to P times the difference of VF and VI. It is often convenient to display thermal processes graphically. For instance, figure in the right shows a plot of pressure versus volume for an isobaric expansion. Since the pressure is constant, the graph is a horizontal straight line beginning at the initial volume VI and ending at the final volume VF. In terms of such a plot, the work W is equal to P times the difference of VF and VI is the area under the graph, which is the shaded rectangle of height P and width VF minus VI. That is the pink shaded part there in the image. Another common thermal process is an isochoric process, one that occurs at constant volume. Figure in the right illustrates an isochoric process in which a substance, solid, liquid, or gas is heated. The substance would expand if it could, but the rigid container keeps the volume constant, so the pressure-volume plot shown in the right figure is a vertical straight line because the volume is constant. The pressure inside rises and the substance exerts more and more force on the walls. Although enormous forces can be generated in the closed container, no work is done. That would be W is equal to 0 joules since the walls do not move. Consistent with 0 work being done, the area under the vertical straight line in the right figure is 0 since no work is done. The first law of thermodynamics indicates that the heat in an isochoric process serves only to change the internal energy. That would be delta U is equal to Q minus W is just equal to Q because W is 0. The third important thermal process is an isothermal process, one that takes place at constant temperature. Lastly, the adiabatic process, one that occurs without the transfer of heat. Since there's no heat transfer, Q equals 0, and the first law indicates that delta U is equal to Q minus W is equal to negative W because Q equals 0. Thus, when work is done by a system adiabatically, W is positive and the internal energy decreases by exactly the amount of the work done. However, when work is done on a system adiabatically, W is negative and the internal energy increases correspondingly. Here is an example problem of an isobaric process with regards to the isobaric expansion of water. 1 gram of water is placed in the cylinder in figure 15.4 and the pressure is maintained at 2.0 times 10 raised to the power of 5 Pascal. The temperature of the water is raised by 31 degrees Celsius. In one case, the water is in liquid phase, expands by the small amount of 1.0 times 10 raised to the power of negative 8 cubic meter and has a specific heat capacity of 4,186 joules per kilogram degrees Celsius. In another case, the water is in the gas phase, expands by the much greater amount of 7.1 times 10 raised to the power of negative 5 cubic meter and has a specific heat capacity of 2020 joules per kilogram degrees Celsius. Determine the change in the internal energy of the water in each case, that would be in the liquid phase and in the gas phase. Reasoning. The change in the internal energy delta U is given by the first law of thermodynamics as delta U is equal to Q minus W. The heat Q may be evaluated as Q is equal to Cm delta T. Finally, since the process occurs at a constant pressure, isobaric because the constant is pressure, the work W may be found using W is equal to P delta V. Here is a table that summarizes the given dataset that are needed in solving this problem. Here are the unknown variables: change in internal energy of liquid, delta U liquid, and change in internal energy of gas, delta U gas. Modeling the problem. Step 1. The first law of thermodynamics. The change delta U in the internal energy is given by the first law of thermodynamics as shown at the right image. Neither the heat Q nor the work W is known, so we turn to steps 2 and 3 to evaluate them. Step 2. Heat and specific heat capacity. The heat Q needed to raise the temperature of a mass m of material by an amount delta T is Q is equal to Cm delta T, where C is the material's specific heat capacity. Step 3. Work done at constant pressure. Under constant pressure or isobaric conditions, the work done is given by the equation W is equal to P delta V, where P is the pressure acting on the material and delta V is the change in the volume of the material. Combining the results of each step algebraically, we find that delta U is equal to Q minus W is equal to Cm delta T minus P delta V. Applying this result to the liquid, we'll have the formula delta U sub liquid is equal to C sub liquid M delta T minus P delta V. Then, we just have to substitute all the needed values into the variables of the formula and we'll arrive at an answer of 130 joules for the change in the internal energy of the liquid. Now, solve for the change in the internal energy of gas. Again, solve for the change in the internal energy of gas. I will just give you 3 minutes to answer. Here is the formula and here is the given dataset. And your 3 minutes starts now. Time's up. May I please ask a volunteer in answering this problem? That's right. The answer is 49 joules. Now for the last activity, identification. Here are the definitions, while here are the answers that corresponds to the definitions on the left. I will just give you 2 minutes in answering this activity and your timer starts now. Time's up. Volunteer, please, for number 1. Number 1 is isothermal process, one that takes place at constant temperature. Any volunteer for number 2? Number 2, that's right, isochoric process, one that occurs at constant volume. Any volunteer for number 3? Number 3 is adiabatic process, one that occurs without the transfer of heat. Now, proceeding to number 4, any volunteer for number 4? Number 4, isobaric process. And that's the end of my presentation. Thank you everyone for participating and listening, hoping that you have learned something from my discussion. This has been Liam Eldoliete saying good day.